Herewith, I am going to discuss the coupled inductors and the inductance calculation. This deals the analysis of the magnetic coupling. The magnetic coupling arises when the inductors are in close proximity. So, the flux caused by the time dependent current in one coil induces the voltage in the other coil. So, magnetically coupled circuits are although electrically separated, but energy transfer takes place through the magnetic coupling. The famous example utilizing this concept is the transformer, which we will be studying in the coming lectures. In this lecture, we will be going through the concept of self and the mutual inductance. We will be analyzing the concept of dot convention, the net inductance calculation for the seriously coupled inductors, and the parallelly coupled inductors will be carried out. We will also be analyzing the concept of coefficient of coupling based on the concept of energy. So, here say the self inductance, only one inductor is there. There is no other inductor in the close proximity. So, this particular inductor is consisting of n number of turns carrying current I of t. So, this particular Faraday's law of induction suggests V is equal to n d phi by dt. This phi flux is because of the current I of t. So, this is represented as by the chain rule d phi upon di into di upon dt. So, this is giving rise to the L di by dt term. So, you made a correspondence and that suggests the L is equal to n d phi upon dt. So, L is the nomenclature which is representing the self inductance, and the reason behind it that it relates to the voltage induced in the coil by the current in the same coil. So, here say the two coils are considered in the close proximity, having say the self inductance L1 and L2, the number of turns are N1 and N2. So, when say L1 is carrying current only I1, it is resulting into the flux phi 1. So, phi 1 is linking the, you can say the little, not linking the secondary or say the other coil, where say the phi 12 is linking the other coil. So, phi 12 is having a definition, the flux caused by the current in first coil is but linking to the second coil. So, going by the same principle, the voltage across the first inductor, inductor 1, V1 is equal to N1 d phi 1 upon dt. This we can extend by the chain rule, so that is giving rise to the L1 di1 upon dt. However, because of this phi 12, there will be an induced voltage in the other coil or say the second inductor. So, that particular value depends on the number of turns of the second coil and the phi 12. Phi 12 it is established by the current I1 but linking the second coil likewise. So, that is giving rise to the M21 di1 upon dt. So, this particular is the induced voltage in the second because of the current in the first coil, likewise you have to understand. So, M21 is associated likewise. Correspondingly, if suppose there is a current only in the second coil, you can find out the nomenclature likewise. So, at this stage we have used the different nomenclature M21 and M12, but we will be deliberating it at the end of, you can say the before the end of the discussion. For the time being, we are considering that this particular coupling or say the mutual inductance term is independent to the direction. So, we can write it the induced voltage in the first because of the current in the second coil. So, M di2 upon dt. Similarly, we can write V2 is equal to M di1 upon dt. Now, as mentioned previously, that the coupling arises when say the coils are in close proximity. This particular is a case when say the time dependent current is there. Now one point which we have to note, that the mutual inductance is always positive. However, we will be seeing that the mutually induced voltage depends on the polarity, or you can say decided by the constructional details. So the mutually induced voltage be computed by applying the right hand rule in conjunction with the Lenz's law. So that particular is also the fundamental aspects. Now we will be analyzing the dot convention. So it analyzes the orientation in which the coupled coils are physically bound. So this particular is important, how they are bound. The dot convention is preferred or marking is used because it is inconvenient to represent the physical details. Just to suppress that and to have the same useful information, the dot marking is done. So you can see a dot is placed at one end of each of the magnetically coupled coils to indicate the direction of the magnetic flux if the current enters the dotted terminals of the respective coils. Likewise. So let us take one example how the dots are to be marked. So this particular is a core. On this we are placing the winding. So let's say one winding is placed which is having two terminals A and A dash. Now we are giving the current. So the current is directed likewise. Now if we are placing the right hand rule into the perspective, the direction of flux will be upward. So we can mark the A as a dotted terminal. There is a choice that we can also mark the A dash as a dotted terminal. So out of this we will be marking the dot to the terminal at which the current is entering. So A is marked as dotted terminal in this. Now for the other winding, we will be simply showing the windings. We will be keeping the direction of flux unchanged, and when say the direction of flux is kept unchanged, the direction of current is marked keeping the right hand rule in mind. So in this way, let's say the thumb is pointing towards the direction of the flux. So we are wrapping it, holding it by the right hand rule and deciding the direction of the current. So the dot is placed at a terminal through which the current is entering. So let's say this it will be B. Similarly, let's say the procedure is for C coil. So here say the flux, like say you are holding it. So in this particular, the direction is to be like this, and we will be marking the C dash as dotted terminal. So the simple concept is apply current to one of the winding and mark the flux direction using the right hand rule. Mark the dot at the terminal through which the current enters. In other windings, orient the current direction while keeping the flux direction unchanged using the right hand rule, and mark the dot in the other winding to terminals through which the current is directed to enter. So you please follow, the current is directed to enter. This is what we are deciding by the right hand rules. Now this is also a reminder that the dots can be marked at all the current leaving terminals as well while following the above procedure, but we will be using the nomenclature of the marking the dots to the terminal through which the current is entering. Now we have to count once the dots are placed whatever say the physical orientation, how the coils are wound around the magnetic core can be suppressed or eliminated. So this particular is the situation. Now we have to account the effect of the current entering or leaving the dotted terminals. So when say the two coils are there, there will be four combinations on whatever say represented on say the left hand side. In this the current is directed to enter. So on current only in the winding 1 is considered, and we will be counting the effect on the other. Where say in the second case the current is leaving the terminals, and we will be counting the effect of mutually induced voltage. So the simple logic here, when say the current is entering the dotted terminal, mark the dotted terminal of other coils as positive. So here say the current is entering, induced EMF will be such that this upper terminal will be positive. So here it is will be having say the same value m di1 upon dt. In this the current is entering the dotted terminal. So this dotted terminal which is at the bottom, that has to be positive, but we are measuring the voltage from bottom to the top, so that's why it is the negative voltage. In this, when say the current is leaving the dotted terminal, so mark the dotted terminal of the second coil as negative, or you can say mark the undotted terminal as positive when the current is leaving the dotted terminal. So that particular procedure is explained. Here say the current is leaving the dotted terminal. This dotted terminal is to be marked negative, or say the undotted terminal as positive. Both will be having the same meaning when say we are measuring the voltage from bottom to the top. Likewise, here say the current is leaving the dotted terminal. So the undotted terminal has to be marked positive, or the dotted terminal has to be marked negative. Likewise, so it is. The same process is repeated. Here say we will be giving you the polarity of the induced EMF separately, and that induced EMF is treated as a source, like is represented as a source, so we can have the same information without making any mistake. Likewise, so this is the equivalent, the two dotted terminal. Current is entering the dotted terminal here. Say there is no current in this, so the induced EMF will be there, but the dotted terminal has to be positive. So that particular is done. Here again say the current is entering, so the dotted terminal has to be positive, or you can say the upper terminal has to be negative. Likewise, so when say we will be measuring the induced voltage between this and the top terminal, it will be coming out to be negative. The same process is repeated when say the current is leaving the dotted terminal. So when say the current is leaving the dotted terminal, mark the dotted terminal of the other coil as negative, or the undotted terminal as positive. So that particular is done. Undotted terminal is marked positive here. Current is leaving the dotted terminal here. So mark the undotted terminal as positive. Likewise, that is done. So this process we will be utilizing while calculating the net inductance of the series and the parallelly coupled inductors. So let's say there is a mutually coupled inductors, they are connected in series. So when say we will be going by the nomenclature that the first inductor is carrying the current I1, second inductor is carrying the current I2, but here say the current is entering, here also the current is entering. We know it that in this particular case the current is common, so that particular will be substituted at the later stage. So when say the current is I1 entering the dotted terminal, so mark the dotted terminal of the other or second coil as positive, that is done. Current is entering to the dotted terminal in the second, so mark the dotted terminal of the first coil as positive, that particular is done. The induced EMF we are able to express with the help of mutual inductance and the rate of change of current in the other coil likewise. Self-inductance multiplied by the rate of change of current in the same coil current. So that has been repeated, but when say I is equal to V1, I1 is equal to I2 is substituted, we will be able to have the expression like L equivalent is equal to L1 plus L2 plus 2M. So this 2M is the factor because of the induced EMF in the second because of the rate of change of current in the first, and induced EMF in the first because of the changing current in the second likewise. The same phenomena, same results will be obtained because in both cases the current is leaving the dotted terminals. So the same result is obtained and they are regarded as the cumulative coupling. Cumulative means the net inductance is now coming out to be L1 plus L2 plus 2M and so on. So net inductance is increasing. The differential coupling, we have to go through the same way, same process, but the differential coupling suggests that the net inductance is L1 plus L2 minus 2M. So when say this differential arrangement is arising because current is entering at dotted terminal in the first in one coil, where say the current is leaving the dotted terminal in other coil. Here say the current is leaving the dotted terminal in one, current is entering the dotted terminal in the second one. So that is a differentially coupled inductors. Now the same procedure is repeated for the parallelly coupled inductors. So they are carrying the current I1 and I2. The KCL suggests I is equal to I1 plus I2. So same case here, say the current is entering the dotted terminal, current is entering the dotted terminal. In these two, for both coils, the current is leaving the dotted terminal. So they are coming out to be the cumulatively coupled inductors case. And when say the current is entering the dotted terminal, the induced EMF in the other coil will be such that the dotted terminal will be marked positive, so the upper terminal will be marked positive likewise. Similarly be the case with the second, so this is marked positive. We will be calculating the net equivalent inductance likewise, which is coming out to be L1 L2 minus M square upon L1 plus L2 minus 2M. How this is derived? This is explained here. So the current, it is done. Let's say the net inductance, equivalent inductance. So this is decided by the net current L eq into di upon dt. This particular is the induced voltage across one of the parallel branch. So that is L1 di1 upon dt plus M di2 upon dt. Similarly will be the case of the other branch likewise. These two equations are used. So let's say the second is subtracted from the first. So that is resulting into the L1 minus M into di1 upon dt is equal to L2 minus M di2 upon dt. As the current is same, so we will be writing it into the differential form. When say we are able to rearrange, the equations are coming out to be like this after eliminating di1 upon dt and di2 upon dt in terms of di upon dt likewise. So here say when say they are cumulatively coupled, this denominator term is having the minus 2m sign. Similarly when say they are differentially coupled, so this particular will be the orientation. Current is entering the dotted terminal, so mark the undotted terminal. Okay, here say the current is entering the dotted terminal, so mark the dotted terminal of the other coil as positive likewise. Current is leaving the dotted terminal, so mark the undotted terminal as positive or the dotted terminal as negative likewise. So that has been done. After that we have done the KCL, so I is equal to I1 plus I2. The KVL relationship is L equivalent into di upon dt is equal to L1 di1 upon dt minus M di2 upon dt likewise. So in this way we will be able to arrange the equations through the same procedure listed in the previous case, and the resulting equation will be like this. Here say it is coming out L1 plus L2 plus 2M in the denominator, so you can say the net inductance is coming out to be lower than the cumulatively coupled coils. Now here says what has been discussed previously, that we considered the M12 is equal to M21 is equal to M. So what is the rationale behind that? So let us prove. Let us take that the initial currents I1 and I2 both are 0. We will be computing the energy while first increasing the current I1 from 0 to capital I1, which is the final value, and then increase the current I2 from 0 to capital I2. Okay. So when say we are increasing the current I1, the I2 is equal to 0. So I2 is 0, I1 is increased from 0 to 1. So induced voltage is L1 di1 upon dt. The power is voltage multiplied by the instantaneous current, so I1 L1 di1 upon dt. When say we are doing the integration, because only the current is increased from 0 to capital I1, this is giving rise to the half L1 I1 square. Now the I1 is kept at the capital I1 level, and the I2 is now allowed to increase from 0 to capital I2. So the power will be by the I1 M12 into di2 upon dt plus I2 L2 di2 upon dt. Okay. So this particular will be there, and this particular is giving rise to half L2 I2 square plus M12 I1 I2. When say we are combining, it is giving rise to the value half L1 I1 square plus half L2 I2 square plus M12 I1 I2. Now this particular procedure is repeated in the reverse manner. So reverse manner suggests increase the current I2 from 0 to capital I2 first, and then increase the current I1 from 0 to capital I1 while say keeping the second current at level I2. So using the same procedure, this particular is giving the energy. So first two terms are the same. The second term here, say the M21 is appearing, in the previous it is M12. However, the energy suggests that when say the current levels are coming out to be the same, it has to have one unique value. So there cannot be two energy levels, and that suggests that it is possible only when M21 is equal to M12 is equal to M. So that is one aspect. Now when say we are considering the cumulative coupling, this particular will be the arrangement. So the same plus sign is appearing. If say the differential coupling is there, then the minus sign will be appearing. This minus sign is, or you can say the differential coupled inductors are giving some useful information. This suggests that the energy cannot be negative. So this particular term has to be always greater than equal to 0. When say we will be rearranging and solving it, we will be getting that M has to be less than equal to root of L1 plus L2. So this particular is suggesting that there is a coefficient of coupling which we can associate, and that suggests K is equal to M upon root L1 L2. So this is further suggesting that the coefficient of coupling value is lying between 0 and 1, because the M value has to be less than equal to root of L1 L2. So the K value cannot be anything other than the value between 0 and 1. So depending on this K, we can associate the coils as tightly coupled, loosely coupled. Likewise, for the perfect coupling, K has to be 1. An example, three inductors are having inductance of 2H, 4H and 6H respectively. The mutual inductances are specified M12, M23 and M13 as 1H, 1H and 0.5H. We have to find the effective inductance. So the standard procedure is they are connected in series. So you will be first adding the self-inductance term L1 plus L2 plus L3. Then analyzing the coupling. So let's say 1 and 2. Here say the current is entering, current is leaving. So that will particular will be resulting minus 2 M12. Then you will be analyzing L1 and L3. So current is leaving, current is entering. So that is also minus 2 M13. Then L2, the current is leaving. Here say the current is leaving. So that particular will be plus 2 M23. So in that way, you will be having the equivalent relationship as L1 plus L2 plus L3 minus 2 M12 minus 2 M13 plus 2 M23, and that particular is giving you the 11 Henry as the net inductance. In this particular, we have to find out the resonant frequency. So first calculate the net inductance L1 plus L2 minus 2 M12. So that particular is giving rise to the 2 plus 4 minus 2, so 4 Henry, and this 2F that is in series. So the resonant frequency you can obtain as 1 upon root of LC. So as a summary, the dotted terminals on the coil indicate the direction of magnetic flux when the current enters the dotted terminals. The example which we considered, the direction of flux was always clockwise when the current was entering to the mutually coupled coils through the dotted terminals. The mutual inductance is positive always. However, the induced voltage is decided by the nature of the coupling likewise, or you can say how that particular coils are bound physically. The high inductance is obtained for the cumulative coupling, whether it is a series connection or the parallel arrangement, where say the lower value is resulted during the differential coupling. On the basis of the coefficient of coupling, we can describe the loosely coupled, tightly coupled, perfectly coupled, or even the uncoupled coils likewise. So next we will be discussing the AC circuit concepts, and you can refer these particular texts for further readings.